Hey guys, welcome back to our channel. This week, we'll be experimenting with one of my favorite elements of all time. Yes, I do mean sodium. A quick disclaimer. Sodium is a highly reactive element that produces dangerous byproducts. Let's get started. Sodium is the second member of the alkali metals on the periodic table. These kinds of metals wish to dispose of their valence electron on their outermost shell to complete the octet rule. This ultimately creates interesting physical properties in these metals. Alkali metals, such as sodium, are so reactive that their physical structures become softer than most metals. Here, I'll be demonstrating this property by cutting sodium with a knife. This sample is old and may seem to not cut so easily, but in the end, the metal will be split in two. Now you're going to notice something about the storage container that's holding my sodium. The element seems to be submerged in some kind of liquid. This liquid is a mixture of kerosene and mineral oil. This is an absolute necessary mixture to have when storing sodium. Due to its reactivity, sodium will react with water in any state of matter. Since water vapor is present in the air, the sodium may simply form an oxide layer or eventually cause an explosion. The oil helps to slow down the oxidation of sodium and keep out any water vapor by the difference in polarity. Now let's get to the chemistry of the reaction we will see a bit later. When sodium reacts with water, it will generate diatomic hydrogen gas as well as aqueous sodium hydroxide. As we know from the last video, hydrogen is extremely flammable and could possibly cause an explosion. Sodium hydroxide is an extremely corrosive base that can burn and blind you. Gloves and eye protection should be worn for this. Just as a reminder, never pick up sodium with your hands without gloves. The sodium will react with water vapor and perspiration on your hands to generate sodium hydroxide. When the sodium is cut, you will see a shiny, unreacted layer that is much different from the exterior of the metal. The dark gray of the exterior is an oxide layer that is formed by reacting with oxygen in the atmosphere. The unreacted layer, however, will tarnish in a matter of minutes. Now for the next phase of our experiment, we will test to see if the sodium really does make a basic solution. Here we have 3 petri dishes, each containing 10 milliliters of water. The first dish has drops of a litmus solution, the second has drops of phenolphthalein, and the third has drops of universal indicator. Each indicator will change to a different color to indicate a change in pH. We will drop a small piece of sodium in each to test for alkalinity. While it is very hard to see, the first piece of sodium generates enough hydrogen gas to push itself against the wall of the dish. Litmus solution has 3 colors to indicate pH. Purple indicates a neutral pH, while pink is acidic and blue is basic. The second piece is the same as the first, but the color change is more obvious. Phenolphthalein, which is commonly used in titration, only has 2 colors. For acidic and neutral solutions, it is colorless, but in a basic solution, it is bright pink or purple. The third piece, as you probably have guessed, did exactly as the other 2. What's interesting about universal indicator is that it has the capability of showing all colors of the visible light spectrum. Red is the most acidic, and purple is the most basic. Green is neutral, and all the other colors are found in between the 3 main colors. The indicator is used to precisely determine the pH in many solutions. Now, let's look at our final colors. The litmus dish has gone from neutral purple to blue to signify an alkali solution. Our phenolphthalein dish has gone from colorless to bright pink, and our universal indicator has gone from green to purple, the most basic pH. We are now approaching the final experiment for our sodium video. This part I guarantee that most, if not all of you, have been waiting for. For our final segment, we are going to throw sodium into a crucible with water. What's dangerous about this is that the sodium actually generates enough heat to ignite the hydrogen gas formed in the reaction, causing the metal to catch fire and then sputter.
There you go. See? That's good. See? Great. You getting the video of this?
What? Careful.
No, it's better.
Thank you guys so much again for watching. Just remember that sodium fire cannot be extinguished with water. Check back with us next week as we try another experiment. See ya!